All right, so now we have two different ways to do concurrent execution, parallel execution on multiple processor cores in our programs. The operating system is providing these two different mechanisms. We can have multiple concurrent processes, or we can have multiple concurrent threads within a single process. And so this, of course, raises the question, what's the difference between these two things? Which one's better? It doesn't quite raise the question of why do we have two things. We obviously have two things because for historical reasons we ended up with two things, but I want to talk a little bit about those historical reasons to then try to answer the question of when should we use which one. So we have these two options for concurrent or parallel execution. We can do processes with fork, or we can do threads with pthread create. Conceptually, we can mix these two things, but you want to be real careful with mixing these two things. If you have a multi-threaded process that then calls fork, the thing that you're going to get a copy of is that one thread that called fork. The other threads are sort of going to vanish, but you are copying the full virtual address space. So there's some risk that you copy the one thread and then you end up with the stacks of the other threads from the process allocated on the new thing. Yeah, you want to be the simplest rule of thumb is if you don't want to think about how to mix fork and threads, the one thing that is definitely safe to do is to call fork and then immediately call exec. But if you call fork and don't call exec and you had a bunch of threads, you have to go figure out what the rules are and make sure that you're dealing with everything correctly. So there's one key difference between these two things. With threads, they're happening in the same process, which means all the threads occur in the same virtual address space, which means that all of the memory in that virtual address space is shared between the threads by default. So there are some advantages to that. It's sort of the actual concept is simpler, right? We don't have multiple virtual address spaces, so we don't have to worry about multiple virtual address spaces. And that also makes some operations simpler. For example, implementing a vector with shared memory with processes is really hard. We may have seen this example in our in-class demo, but if you have a sort of vector or variable length array data structure, if you have it allocated with threads and you're sharing the pointer, then any thread that has access to that pointer will have access to the latest version of the thing, even through resizes. Whereas with processes, you can't really implement realloc with mmap. Once you've forked, new allocations are not shared. Only the allocations that existed before forking are shared, unless you go through the effort of saying that you're not map anonymous, and therefore you're backed by a concrete file with a name, and then you have a bunch of other complications. But there's a huge disadvantage, and that is that now you're 100% data races. With processes, we have this advantage that the only stuff that is shared is the stuff that was allocated with mmap with the map shared flag before fork was called. And that means that actually programming with processes can end up being simpler because there's this whole category of bugs that you don't have to worry about unless you opt into it. So let me go a little bit through the history of how we ended up with these two things. Now, initially, we weren't worried about parallelism. That wasn't the point of either of these concepts. We didn't have multi-core computers. We didn't even have multi-processor computers with multiple processor sockets that we could put separate processors in. And so in like 1978 or something, 1986, there was no real worry about being able to schedule work on multiple processes because you couldn't. If you had multiple things happening concurrently, it was simulated concurrency by sharing time between processes or threads on a single CPU in the computer. But we did want that concurrency. So one sort of branch of this was the sort of Unix style branch, and that is the idea that if we have a machine that's being shared by multiple users, then obviously we need to have the multiple users be able to concurrently execute separate programs. And at that point, extending it to say that a single user can execute multiple programs concurrently isn't that big a change. We were talking about, we have the shared curry login server, and that's a perfect example of the sort of situation that a Unix-style system was initially designed for, where you're going to have one central computer, and then it's going to have maybe a dozen people who use it. In a situation like a university computer science department, maybe you'd have 100 people using it, but then it's going to start to bog down because you only have the one processor core and everybody has their homework to do at the same time. But simply, once you have two users that want to use this machine at the same time, being able to run multiple programs at the same time is important. They're going to run different programs, so we want processes to do that. On early Windows and Mac systems, we had the idea of running multiple processes, but they didn't really run concurrently. Usually you'd have one foreground job in your graphic user interface, and there wasn't really a reason for background programs to do stuff. There was some mechanism to make that happen, but it wasn't the sort of the case that the designers were focused on. We're not talking about really early Windows or really early Mac. I'm talking about like Mac OS 7 and Windows 3. And the idea was, the reason that you needed concurrency is because the program was logically doing two things at a time, because we had a graphic user interface. So maybe we are, so simplest case, we have a image editing program running. We've selected effects blur from the menu, and we have a slow computer and a big image, so blur is slow. And the operating system and the program wants to present us with a cancel button, because this operation is going to take 10 seconds, and if we did it by mistake, we want to be able to press cancel and revert to the previous version of the image. But we have to both have the logic for the blur running, which is doing the processor-intensive work, and we have to have something sitting there listening for the event if we click in the GUI, so that we can actually cancel. And that's sort of the motivation of threading on early desktop-style operating systems. So this is sort of a shared system or server-type machine, whereas this is an early desktop. So we have two different sort of kinds of problem that we're solving, but you can see that this ends up being the same vague idea of something. But there's one big difference here. On the server shared system, it is preemptive multitasking. The program doesn't get to decide whether it's running or another process is running. The CPU time is going to be shared by the operating system between the programs. The program will get a little bit of time to run, and then it will be stopped, and then another program will get some time to run. So one thread would run for a little while, and then it would have to call yield to give other threads a chance to do something. And that includes that case with the blur operation. So the blur operation would have to do a little bit of work and then call yield to make sure that the graphic user interface didn't freeze. And that was a bug that you would have frequently in programs, is that the graphic user interface would freeze during a long-running operation because someone forgot to put in their yield calls. And eventually, the operating systems updated to have preemptive scheduling just to make it so that programmers couldn't leave out the yields. Even though cooperative concurrency is a little bit faster. If you're doing preemptive multitasking, the operating system has to stop every running program every once in a while, and then give every other program a chance to say that it wants to do something or not. Whereas with cooperative concurrency, we only have to switch back and forth when the program opts in. And in addition to calling yield, sometimes we have an implicit yield when I/O happens. That's still how some programming environments work today. And by the 90s, that was how that worked. So this led into the situation that we have currently, when we started to get into multiprocessors. So by the mid-90s, having a server, especially a server that was going to be on the internet, have multiple processor sockets was pretty common. I remember putting in a couple of servers for a web hosting customer at a company that I was working for in 2000 that were dual core. That customer didn't have any budget at all. It's just if you bought a server in 2000, it was going to have 2 processor sockets. But they were readily available in even 1997. But desktop computers didn't really end up having multiple sockets frequently. You could get workstation systems with like 2 or even 4 sockets, but normal sort of common person desktop computers didn't start to see this, and especially not laptops, until around 2005. Now, interestingly, like Linux was primarily used on servers, but it didn't get proper preemptive multi-threading until really late. In fact, so Windows and Solaris, which was a common commercial Unix, had good threading support, and so Windows took advantage of multi-core or multi-processor systems in single applications by having multi-threading. If you want to do stuff in parallel, you'd run a multi-threaded program. Solaris, you had the option of either doing multi-threading or you could call fork. But on Linux, if you wanted to do concurrent execution or you wanted to run software in parallel, you'd just call fork. And you'll note that this means that so Linux actually got good threading support around 2002. And this has the interesting property that because Linux was the major web server operating system from 1996 through, even through today, most web servers are running Linux. But in the like big web boom of like 96 to 2004, Linux was like 60 to 80% of the web servers out there. And it was doing this on multiprocessor machines without having good threading support. And so it had to fork to be able to accept concurrent requests coming in. And so that means fork got super optimized on Linux. We're talking the most common use case of a Linux system was these web servers, and the way the Apache web server worked was that it forked on every incoming request. Concurrency. Nope, still spelled it wrong. Forked on every incoming request, and the reason for that is because if you have two incoming requests, say someone requests a download of a 500 meg file from a website, and then another person comes along 20 milliseconds later and requests to view index.html, which is 2K, we don't want to have the small request that came second blocked waiting for the big request that came first to complete. We want to be able to have both of those things happen concurrently, and that'll work nicely if we have two separate processes for the web server that will get scheduled by the operating system, and the fast request can finish fast and the slow request can finish slow, and everybody's happy. But the result is that we have this super optimized fork. Now, the way that threads are implemented under Linux is basically just an extension of fork. Threads didn't get a whole new set of stuff put into the kernel to support a big differentiation there. Threads are just processes that share a process ID in a virtual address space. That's all threads are under Linux. Under Windows, and maybe under Solaris, although I haven't spent a lot of time recently noticing people using Solaris. But under the systems that had threading support, threads were a different thing. But under Linux and probably things like FreeBSD, therefore probably things like macOS, processes and threads are internally very similar in implementation. They share a lot of code. And so the performance difference ends up being really small. Doing pthread create might be a little bit faster than doing fork, because you don't have to copy the page table. And that's real work that you actually have to do, but it's not slow work. It's fast enough that this plan for Apache was okay. We've since moved to programs being a little bit more complicated, taking advantage of threads, taking advantage of non-blocking I/O for web servers. But Apache was the server that drove the rise of the World Wide Web, and fork was good enough for that. On the other hand, Windows focused on threads, so creating threads on Windows is much faster than creating processes, and in fact, we end up with this thing where the fastest thing you can do is create a thread on Windows. The next fastest thing is creating a thread on Linux, which is then only slightly faster than creating a process on Linux. And creating a thread or process on Linux is much faster than creating a process on Windows. So around 2005, we got multi-core processes, so every desktop machine needed fast parallelism. And again, on Windows, that was threads. That was the thing that you could go to get a parallel speedup. And on Linux, by that point, you just had a choice of threads or processes, and whichever made more sense for sort of the structure of your application is the thing that you did. So that probably means that if you're picking something in general for the purpose of parallel speedup, threads should probably be your default unless you're sure you're on Linux and want the advantages of not sharing a virtual address space. But sort of rule of thumb, If you want data shared between your concurrent stuff, threads are going to be a little bit more convenient. If you want to make sure that data isn't shared, as in the Google Chrome web browser where we have a process for each tab, you want processes because then the MMU and the virtual memory system are sort of protecting your processes from each other. All right. In a minute, I'll be back with one more example, I think.